Welcome back. We were discussing the BJT biasing configuration. In the previous lecture, we discussed about the fixed bias. This lecture, we will see first about the emitter bias configuration and then the other biasing techniques. When we discussed the fixed bias configuration, we have discussed about its limitation. So we need to improve the stability of the fixed bias configuration. So that is the objective. So the key features of having the emitter bias is that we will be adding one resistor RE. So if we remember, in the fixed bias, the emitter was grounded directly, but in emitter bias configuration, we will add one resistor RE to the emitter circuit. Greater resistance lead to temperature variations and parameter shifting. So this will help in the temperature fluctuation and when there is a shift in the parameters. So we can see in the circuit that there is a resistor RE which is connected to the BJT. Earlier in fixed bias, this was directly grounded, and this would result in consistent performance under the varying condition. The resistor RE would introduce a feedback that stabilizes the circuit. Also, it impacts the base and the collector emitter loops. Let us do the analysis from the base emitter loop analysis. So the DC equivalent of the emitter network, we take the supply voltage VCC split into two parts so that we can do easy analysis. And then in the base emitter loop, we can write the KVL equation. So the KVL equation would be the total voltage which is supplied by the VCC and the drop which is associated with the different parts of the network involving the resistor of the base and the emitter resistor. There is a voltage drop in the base emitter junction also. We also know that the emitter current is beta plus 1 times the base current. So putting this equation here in the first one, we get what is the base current. So the base current, if we compare from the fixed bias, there will be an additional term here which is appearing, that is beta plus 1 into RE. This is in the denominator which will improve the stability of the fixed bias in the network. So we are having the emitter bias network which is having one additional term in the denominator of the base current, and that improve the stability. If we talk about the equivalent circuit, if we see it, then it appears as if the resistor RE which is in the base circuit has changed into beta plus 1 into RE, and this is due to the reflection effect in the circuit. So the resistor RE multiplied with beta plus 1, this is a quite a significantly larger value because the beta value lies in the range of 50 or more. So if we see the input resistance of this network, we can say that beta plus 1 into RE will be the input resistance. So the greater the input resistance, it will offer the better temperature stability and it will reduce the sensitivity to variation in beta. So here we can see the network which is the reflected network having the resistor beta plus 1 into RE. Beta value lies greater than 50. So this value is very high. And if we apply the Thevenin's network, then we can find what is the input resistance of the emitter bias network. If the same type of analysis we do from the collector side, that is collector emitter loop analysis, we apply the KVL equation in the collector emitter loop. So we will get the potential drop in the different parts of the network. We also know that the emitter current is approximately equal to the collector current. So we can remove the equation of the emitter current in the first one and get what is the voltage of the collector to emitter region. Also, certain other expressions we can have, that is what is the voltage across the emitter, that is equal to IE into RE. What is the voltage of the collector and the voltage of the base, so that we can obtain from the equation of the different voltages. So different forms we can get for the collector voltage, either in the form of VCE plus VE or in the form VCC minus ICRC. So depending upon what is available, the data, we can use any of the expression of the collector voltage and the base voltage. So either of the expression can be utilized. The voltage level and the biasing point when we discussed, then the maintaining the collector to emitter voltage above the saturation voltage will ensure the linear operation of the BJT. The proper selection has to be done for the emitter resistor and the collector resistor, and these would determine the collector to emitter voltage which would result in better stability of the network. It stabilizes the operating point by providing the negative feedback in the circuit and also ensure consistent operation despite the changes in temperature or transistor parameters. So even there is a fluctuation in the temperature or there is change in any of the parameter, but there would be the stability in the network for common emitter configuration. The next type of biasing that we discussed is basically the voltage divider biased. So here we saw that when we try to find the Q point by biasing the BJT, it will set the operating point for consistent performance. All the previous configurations depend upon the current gain beta. Beta actually it is a temperature sensitive parameter and varies especially in the silicon transistor. So desire for the bias circuit that is less dependent on beta. So beta fluctuation has to be avoided. Voltage divider bias would provide the stable operating point despite the beta variation. So even there is change in the beta, if we use the voltage divider bias, it will give you the stable operation. Proper circuit parameters lead to beta independence, and then we get the collector current and collector to emitter voltage at the Q point. So in the circuit configuration of voltage divider, we can see that there are two resistors R1 and R2. So these resistors are basically forming the voltage divider network. So the current ICQ and VCEQ, that is the collector current and collector to emitter voltage at the Q point, would result in the stability of the network. So here you have the Q point, and corresponding to the Q point you will be having the ICQ and VCEQ current and voltage when we draw the graph between the collector current and collector to emitter voltage for a fixed amount of the base current. So despite there is a change in beta, the collector current and the collector to emitter voltage at the Q point would remain fixed. So it is not going to change. Now let us do the analysis. So in order to do the analysis, we will take the help of Thevenin's theorem and we obtain the resistance Thevenin and the voltage Thevenin for the network in the voltage divider bias circuit. We also apply the KVL equation in the loop of the Thevenin's theorem circuit, and we know that emitter current is beta plus 1 time the base current. So if we substitute this current emitter here in the expression of KVL, we will be getting what is the base current. So here also we see that in the denominator you will be having an expression of beta plus 1 into RE, and the collector to emitter voltage would be from the KVL equation. Again we get VCC, that is the input minus the total drop. Other expression of emitter voltage, collector voltage and base voltage would be obtained by similar method as we have discussed in the emitter bias network previously. There are certain benefits of voltage divider bias circuit. It minimizes the temperature and beta sensitivity. So we saw that even there is a change in the beta, in the voltage divider bias there is no major changes. The Q point is stabilized, which ensure consistent circuit performance, and this is versatile and widely used in the practical design. So among the BJT biasing network, we have discussed the fixed bias, the emitter bias and the voltage bias. Another two important configuration, we will discuss the collector feedback and the other one in the coming lecture. Thank you for now.